Hey, there's that fire alarm test going off again. Um, the I have to tell you, I'm not going to lie, that is getting slightly annoying. If you're thinking to yourself, wow, that's annoying, watching this video, imagine what it's like for me being here. It's pretty loud. All right. So, if you have not yet done Collision Worksheet 1, you should definitely go back and do that. And if you have not attempted Collision Worksheet 2 by your own big kid self, then you should do that first. So this, it's all the same stuff we were doing on that Collision Worksheet 1, and just a little bit more practice with that. Okay, talking about practice. So go ahead, and if you haven't tried it yourself, pause the video please and do that. If you have and you're checking your answers, well, let's get to it. Okay, so I got car A traveling east at a constant velocity of 10, and the instant car A reaches car B. If you're wondering about this, like what's with this, like the instant car A reaches car B? That's just so like we're saying like they start at the same place, right? 0. They're there at the same time. Who's traveling at rest? And car B. That's a funny. The who. Car is a who. It would probably be like that or which. Is traveling at rest. Car B begins to accelerate at 1 meter per second per second. Okay, so let's see. What would the those position equations be? This is constant velocity, so it's just that constant velocity times time. And then this one, again, remember this is the delta x is equal to 1/2 a t squared plus vi t. If we had an initial position, if this was not starting at 0, then you'd have to break up the delta x, and to get just x, you'd have to add the initial position over here. Let me explain what that means. So if you want to know, like, where's your position, like your final position, or your position, like, after some amount of time has gone by, minus initial position, that's what delta x means, right? The change in those. So just in case we ever run into a problem where there is an initial position, you can just break this up and say, okay, I can still make a position equation. I just need to move this over to the other side, like that. So if there is an initial position, you just have to add it on here. But there isn't. It starts at 0 here. So same thing with this one, by the way. If there was an initial position, I could put it here, just like you did with those toy cars. So this is going to be 1/2 a, and the acceleration is 1, so that's just 1/2 times 1. That's meters per second squared times time squared, and then plus the initial velocity, but that's 0 times time, so that goes away again. Okay, so table. Here's my times. Let's go 0, 1, 2, 3, 4, and 5. That's enough, I think, to get an idea what's going on. So this car A is going 10 meters a second, so that's just going to go up by 10s, since this is just going up by 1s. And then car B, let's see, if I plug 0 in, I get 0. If I plug 1 in, I get 1/2. If I plug 2 in, I get 4 times 1/2. So it looks like this table is not going to go far enough to see where car B. Is it a given? Is car B definitely going to catch car A? Think about that. If it has some kind of acceleration, like what if this acceleration was a really, really small number? Like could it maybe never catch that car A? Or is it always going to catch car A? What do you think about that? The answer to that question is this: if it has a positive acceleration, it doesn't matter how small that number is, it will always catch A eventually. Because if you imagine a straight line, which is what this looks like, if you graph position versus time. It doesn't matter how incredibly slowly this thing might bend upward. If it's bending upward, it is eventually going to cross this line. And that's the truth, not fake news. Determine where A and B meet. My table didn't get me there, but that's okay. I like to do it algebraically anyway, so I set those equal to each other. 10t, that's this one, is equal to 1/2 t squared. So get everything onto one side. I'm going to multiply both sides by 2, so I don't have to look at that fraction. Not that 1/2 is a terribly scary fraction to look at. So it looks like my two cars are at the same place at time 0 and time 20. And time 0, of course, that's when they start. I'm not really interested in that. I'm interested in that where car B catches up to. And let's see, if this goes 10 meters every second, then that's going to be at 200 meters. And I can just go ahead and plug that 20 in here to double check that. 20 squared is 400 divided by 2 is also 200. Oops, that's off the screen. There we go. All right. This isn't that hard. Number 2. Two cars are heading toward each other. Whoa, that's different. Okay, don't worry. Take a deep breath. We can do this. As shown in the diagram, car A starts from rest here and accelerates east. That means its acceleration is in the positive direction at 2 meters per second per second. Car B starts from it starts over here and is going west. I guess that must be in the negative direction, right? So I'm going to make that negative, right? It's because it's going that way. If this is positive, if this is the positive direction, then the other way must be the negative direction. All right. So how do we do this? Well, let's see. My equation for this is going to be just like all the other ones that we've done. It's 1/2 times the acceleration, so that's just 1, times t squared. Its initial velocity is 0, so the plus VIT, that term is going to go away. And that's good. How about for B? I'm going to leave that blank for just a sec here. So here's my times. 0, 1, 2, 3, 4, 5. I'll do that again. If I don't make it all the way to the time where they're at the same place, that's okay, because we're going to do the algebra here. So let's see. So car A at time 0 is at position 0. 1, 2 squared. So I'm just going to get the squares, so I'm just multiplying by 1 every time. So that's going to be 4, 9, 16, 25. How about car B? Well, let's see. At time 0, it starts at position 100, right? It's starting here, not over here. So they don't have the same position at the start. And then it's going 5 meters per second, but this way. So after 1 second, what would its position be? If you said 95, you're right. And then it's going at a constant velocity, so the position, every 1 second that goes by, the position decreases by 5. So my table doesn't show, it doesn't go far enough, but you can see them getting closer and closer together. Okay, now what's the equation for this? Well, we've done this before. It's going the negative direction, so that's negative 5 meters per second times time plus the initial position. And you can see how plugging different t values would get you what you need. Right? This is an example of position is equal to velocity times time plus initial position. And this is from Unit 2, constant velocity, right? That's the same thing as what we were using for using here, but the initial, that just started at 0, right? So that plus the initial position didn't show up. And of course, the negative sign here is super important that you have that because they're going opposite directions. If you don't, what if this one was going 5 meters per second that way? Will this car eventually catch that one? Yes, because it's accelerating. But you're going to get a totally wrong answer. If you did everything else right here, but you made that plus, then this is going to be going 100, 105, 110, and that is not what's happening here. All right, so on a separate sheet of paper, you do graph paper solution to this. You could do that. I think to do the graph, I'm just going to make a sketch of the graph. I mean, if you're going to do all this work and get the equations, you know, why wouldn't you just use some algebra? So just a rough sketch of this. It looks like all the other ones. Oh, actually, it doesn't look like all the other ones. Sorry, that's totally wrong, isn't it? Because this one starts at 100, and it's going in the negative direction. And you could do a little bit of math. It's not too hard to see, I think, that it's going to, since it's going 5 meters every second in that direction, it's going to take it 20 seconds to get back to position 0. And then this one is going to curve up. I don't really know where it crosses. You could extend the table out, make a more detailed graph, and get a good idea. I mean, I think you're going to see it in your table, right? But you could see in the graph also, like this is the time that we're looking for when they're at the same place, and then this here is the position that we're looking for, right? So graph's going to look like that. How about the algebraic solution? We like algebra. All those math classes that you took. Finally get to use that stuff, right? So here, this is 1t squared. And here, I've got minus 5t plus 100. I saw a cartoon the other day. Some friend of mine who knows I'm a math teacher, math, science, that sort of stuff, sent me this cartoon. It was like a classroom, and like here's a teacher up here, like writing on the board. Like who does that, writing on the board anymore? And then writing some math up there, x equals 2 or whatever. And then there's a bunch of kids sitting out here, and there's this kid, Johnny, whatever, and he's got his hand up, and he's saying to the teacher, he's like, "Hey teacher, are we ever going to use this algebra?" And the teacher looks back at him, and the teacher says, "You're not, but one of the smart kids might." I mean, that's kind of like, it's a little bit messed up. I guess teachers shouldn't laugh at that. But here we go. I mean, I guess you guys are the smart kids. Look, here you go using that algebra. So, for better or for worse, I guess you guys are the smart kids. So, let's get everything on one side here.
Attention everyone, just letting you know that there's going to be a pause with the testing of the fire alarms. There will be a pause until 10:30.
Well, isn't that nice? Of course, they interrupted that pause with an announcement, but that's all right. So I got everything on one side here because that's what my algebra teacher told me to do. And what do you do now? I guess you could try to factor this, but I'm pretty sure that this doesn't factor. One of the great lies of algebra is all these factoring problems that you're given. Like factor this, factor this. If you just make up some numbers here, it's overwhelmingly likely that things don't, in fact, factor. That you're going to have to use the quadratic formula or some other method. You don't have to bust out the quadratic formula here. You could if you wanted to. My recommendation for you is when you get something like this, just like we were doing the other day with our acceleration problems. I think in particular with the free fall problems we were doing a lot of this. I'm just going to graph this right here and then look for the zeros. If you get everything on one side, then you can graph it and look for the zeros because you have it set equal to 0. So x squared plus 5x minus 100. And I don't know what my window is set up to be right now, so I'm going to go ahead and hit window first. I don't want to just do some random crazy window. So 0 and 10, that's probably going to be good. Do we think that these two things are going to intersect here or crash into each other in the first 10 seconds? I think that that's looking pretty likely, right? Because this one's bopping up pretty quick and this one's coming down. So I think that that's probably good. So I have my Ymin and Ymax set at just -1 and 1. All I need to see here is the axis. I just need to see where it crosses. So I don't need a whole lot of Y values to look at. So that looks good. And boom, there it is. So that looks like it's in between 1, 2, 3, 4, 5, 6, 7, 8. It looks like it's in between 7 and 8. If you were not sure at all, you can just widen that up a little bit. You say, well, 7 and 8, how about we go between 6 and 9, just to be sure, or to be safe. So second, calculate my 0. It's in between 6 and 9. And it's about 7.8 seconds. All right, and where does that happen? Well, I can take that 7.8 and I can plug it into either one of these. I'm going to plug it into both just to check because I'll feel awfully good about my answer if I get the same thing from both equations. So plugging in 7.8 into this one, right, my position equation for car A, it's just 1 times t squared. So 7.8 squared is about, I'm going to call that 61. And I'm going to confidently write that down as the answer, but before I get on with my life, I'm going to just plug that in here too. -5 times 7.8 plus 100. Now, I'm not expecting to get exactly the same number because I did round that 7.8. So I should get something very close to that. Oh, 61. How about that? So there it is. And just to, since we're all here together, if you did want to see this graph on your calculator, we can do that. I have here the position of car A is just 1 times t squared, and the position of car B is -5t plus 100. Now before you go hitting graph, I'm going to go to my window, and just making this sketch here, I think I realized that from 0 to 20, that's how long it takes for car, the constant velocity one, I think that's car B, to get back to position 0. So I'm going to go ahead and make this axis here, I'm going to go from 0 to 20 on my horizontal axis. And then on my vertical axis, I know that this one starts at 100 and it's going this way, so between 0 and 100, that's enough to see everything that's going to happen. So from 0 to 100, you don't have to change this y scale, but that just tells you, tells the calculator where to make the little tick marks. Probably if we go by ones, it's just going to like black out the whole thing because they're going to be so crowded together. So I might go by tens. It's not going to mess up the graph, except the axis isn't going to look as nice if you don't do that. All right. There they are. So my graph here was okay. They should have intersected more like here. But there you go. Just in case you care about this, If you're wondering, like, why did my calculator graph those at the same time? If yours did like this and then it did this one, or vice versa, in the mode here, the default is this sequential. That's where your calculator graphs one graph at a time. And simul is short for simultaneous, where it graphs them at the same time. So if you care about that, this is an old TI-83. If you scroll down, you probably have more options. You can make them color, or, well, it depends on what calculator you have, I guess. So sequential, that looks like, does that one, then it does that one. For the purposes of physics, if this is time on this axis, which it often is for us, it's kind of cool to see them happening together, because then you have that sense of them kind of like moving together. So anyway, that's the thing. Have a great day.